Hello and welcome back to Ordinary Differential Equations, the video series where we talk a lot about solving differential equations. And in today's part 16, we will look at some special solutions that have some nice orbits in the phase portrait. In particular, we will talk about fixed points and periodic solutions. However, as always, before we start, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Please check out the link in the description to see how to become a member on Steady. Because as a member you have a lot of advantages. For example, you can download the PDF versions and quizzes for the videos. Okay, then I would say let's immediately start with our system of ordinary differential equations. And you know, we always write it as x dot is equal to v of x. And there you know, v is a vector field that maps a subset of Rn into Rn again. Moreover, often we assume that it is a locally Lipschitz continuous function. And as we have already learned, we can simply sketch this vector field and then we get the phase portrait in the end. In fact, the phase portrait is just a collection of the orbits the solutions make. So please note, an orbit is just an image of the solution, so we don't see the time variable, but we see the points in D that are hit by the solution. And as we have already discussed in the last video, we can have some nice orbits like such a circle or just a dot. And in fact, these are the ones I want to define now. And it turns out that these orbits come from global solutions, so solutions that are defined on the whole real number line. Hence, they make sense for all points in time. And here please recall, the only thing we want for the solution is that it satisfies our system of ordinary differential equations. Therefore, it necessarily has to be differentiable. However, we have already learned that in general, a solution is not a global solution. But in addition, we also learned that we have a global solution if we have a constant solution. And now such a constant solution will be called a fixed point. Hence, by definition, we have that alpha of t is equal to alpha of 0. And obviously, this holds for all t then. And you should see, this happens exactly at the point in D where v of this point is equal to 0. Therefore, often this point in a domain is also called fixed point. Indeed, the differential equation tells us if we start at that point, we can stay at that point as long as we want. Hence you can remember a fixed point is always a global solution. Okay, then let's go to the next nice orbit there, which is the periodic one. Therefore, we also call this solution a periodic solution. This means after a fixed time, which we would call a period and be denoted by capital T, the solution alpha will just repeat itself. More precisely, if we add the capital T to any point in time, the solution alpha gives the same value. And also here, this should hold for every point in time t in R. And in this case, we call capital T a period of the solution. And it's important to know that we don't have to choose the minimal period here. For example, in the case of the circle, the minimal period would be exactly the time we need for one rotation. But of course, we could also choose t here as the time for 2 rotations. Therefore, if you see the definition here, you should see that the fixed point is also a periodic solution. Some people don't like that, and then they only use periodic for solutions that are not fixed points. And indeed, for fixed points, we are not able to find a minimal period at all. Simply because every capital T will work for the definition. However, for all other periodic solutions, there exists a minimal period. Okay, so now we can conclude that the orbit of a periodic solution is closed and we go around infinitely many times. And since we already know the general phase portrait for a locally Lipschitz continuous vector field V, we now have 3 cases. And these I want to put into the next proposition. So we take V as a locally Lipschitz continuous function and then we consider the initial value problem. We know the initial value problem has a unique maximal solution alpha. This means for a chosen point x0 in the domain, we consider the solution that is at x0 at the time 0. Please recall, this is also how we have defined orbits in the last video. And therefore, we can also use what we have learned about the orbits. We know two orbits cannot cross, so we can have the case that alpha is injective. So this means alpha does not hit a point in D more than once. However, we have also already discussed that this actually can happen. Namely, exactly in the case that alpha is a periodic solution or a fixed point. And this is important to remember because these are all the cases we can have for solutions. So first we have the injective solution that can just go somewhere. Then we have the fixed point that just stays at the same point for all time. And we have the periodic solution that goes around and around. Moreover, only the injective solution might not exist for all time. So only there the domain of alpha could be smaller than the whole set R. Okay, in order to visualize all of that, I want to look at an example with you. And indeed, if you know some physics, some mechanics, you might recognize this one as an important one. I want that the second derivative of x is equal to minus sine of x. This is exactly the equation for a pendulum like we have it in mechanics. However, as always for our theory here, we want to transform that to a system of first order. And you know how to do that. We just introduce x1 and x2. And then the derivative of this vector is equal to x2 and minus sine of x1. So indeed, the right hand side here is our vector field v. Therefore, this is something we could sketch to see some orbits already in R2. However, before we do that, I first want to show you a trick that can be helpful for finding solutions of such a system. The trick is to find a nice function f such that the solutions are on the contour lines of f. This means f maps R2 into R. And then if we put in a solution alpha of t, then what we want is that this is constant for every t. And obviously this should be the same constant for every t. This is quite nice because then the contour lines of f already tell us everything. So for example, if you plot such contour lines, you would see we could have a fixed point where we just have a constant here, and maybe you also see periodic orbits and so on. So the contour lines already tell a lot. But now the question is, how do we know that we have such a function f, and how does it look like? And to answer that, let's look at a very important calculation. Now, the fact that this here is constant for all t is equivalent to the claim that the derivative of this function is equal to 0 for all t. So you see, we have to assume some differentiability properties as well. However, in that case, we can simply apply the chain rule, which means we have the standard inner product of the gradient of f together with the inner derivative, which is given as alpha dot. And there, what we can use is that alpha is a solution of our ODE. This implies that alpha dot is equal to v of alpha. So this is exactly what our solution of the differential equation does. So in summary, we can say what we have to find here is a function f which gradient is perpendicular to v. And this is not too hard because we can try some things out. So for example, we could say we take 1/2 x2 squared minus the cosine of x1. Because then the partial derivatives coincide with the things we have in v, and then we just have to fix the sign in some sense. In fact, here I can already tell you, we have it, gradient of f is perpendicular to v. And because of this nice property and the calculation from before, we have the nice property that f of a solution is constant. Hence, this implies plotting the contour lines of the function f already gives us our phase portrait. Moreover, we also know how to find the fixed points because these are the points where the gradient of f is equal to 0. Exactly at these points, the solution can stay constant. Now, the gradient of f is not complicated, it's simply sine of x1, and the second component is x2. And for fixed points, this should be equal to the 0 vector. Hence, to find them, we already know that x2 has to be 0. And moreover, x1 should be a multiple of pi, because these are exactly the zeros of the sine function. And of course, k has to be an integer here. So going back to our picture, to the contour lines of f, it means that we find our constant solutions, our fixed points here, and so on. So we find infinitely many if we continue in the x1 direction. Moreover, you should see that we also find periodic solutions if we go around such a fixed point. In fact, this represents the normal movement of a pendulum, which goes around and around. And the fixed points represent the points where the pendulum stands still. And in fact, we also find fixed points here. However, these are really close to a periodic orbit and therefore a little bit strange. In fact, they represent the cases that the pendulum stands upside down. So you would say this is highly unstable, but still a solution of our ODE. So putting that together, the fixed point just means that the pendulum does not move at all. And as I already said, a periodic solution here means that the pendulum goes back and forth. Indeed, this is the normal pendulum behavior we want to have. It's a periodic thing and it goes on forever. However, I should tell you that we also have the third case here, so injective solutions. They are really high or low in the x2 variable, which represents the speed of the pendulum. In other words, the pendulum is so fast that it does not go into the periodic behavior. So it's not a normal pendulum, it just goes around and around in circles. But still, it's an injective solution because we have x1 and x2 as variables. Hence, this pendulum already represents the three kinds of solutions we can have. However, as we have seen here, a fixed point can be distinguished even more. There could be a fixed point which is stable if we wobble around, or one that is not stable if we wobble around. Wobbling here around simply means what happens to the solution if we change the starting point a little bit. And for a stable fixed point, we stay in the neighborhood of the original solution, but for an unstable one, we completely go away. Hence, what we will do in the next step is to zoom in at such fixed points and see what happens in a local neighborhood. And not surprisingly, there we can do a linear approximation. And therefore, ordinary differential equations that are linear are really important to understand. So exactly this we will discuss in the next video. So I really hope we meet again and have a nice day. Bye bye.